Today's lecture will be on precipitation and complex ion equilibria. We'll start as usual with some reminders. There will be a new homework set that will be due next Wednesday, and tomorrow class time will be devoted to completing a worksheet that corresponds to this lecture. So you can get 3 bonus points just for completing the worksheet in class, and I will also be offering up to 5 bonus points if the worksheet is done well. So you have some incentive to get some bonus points on the last exam and to actually go into class and work with your peers to get a good score to do well on the worksheet. So we'll start with a review question. In which solution is barium sulfate going to be the most soluble? We have 0.1 molar barium nitrate, 0.1 molar sodium sulfate, and 0.1 molar sodium nitrate. So take a minute and think about that to yourself. And hopefully you're thinking about the common ion effect. So we know that our equilibrium for barium sulfate is going to be barium sulfate solid dissolves to form Ba2 plus SO4 2 minus. So the common ion effect tells us that a solid will be less soluble when a common ion is present. So we want to look for things that do not have either barium or sulfate present, and that leaves us with only C, sodium nitrate, and that will be the most soluble because there is no common ion effect there. So now we're going to use the common ion effect to calculate the molar solubility of calcium hydroxide in a solution with a pH of 13, which will then compare to the molar solubility of calcium hydroxide in pure water. So the first thing to note is that this solution has a high pH, and a high pH suggests that there's going to be a high concentration of hydroxide. And this is important because if we think about our equilibrium expression, that'll be calcium hydroxide. It breaks down into calcium 2 plus and 2 hydroxide ions. So having that high concentration of hydroxide will affect how soluble the compound will be. So we need to find the concentration of hydroxide first. We can do this because we're given the pH. We can then find the pOH, which will be 1. And then by raising 10 to the power of the negative pOH, we can get that our concentration of hydroxide is 1 times 10 to the negative 1 molar, or we can also write that as 0.1 molar for ease. So next we'll have to set up a rice chart. Again, we start with our reaction. We have calcium hydroxide. Remember, calcium is 2 plus, so you're going to need 2 hydroxides to balance the charge, and that produces calcium 2 plus 2 OH minus. We know for our initial concentration we're going to ignore calcium hydroxide and that we have no calcium to start with, but that we do have 0.1 molar hydroxide. For our change in equilibrium, it will be minus X for calcium and, plus X for calcium and plus 2X for hydroxide. Don't forget about the coefficients there. And then finally, that gives us our equilibrium concentrations you get by adding the initial and the change. So X for calcium and 0.1 plus 2X for hydroxide. So then we need to plug this into our equilibrium expression. KSP will be equal to the concentration of calcium times the concentration of hydroxide squared. Again, don't forget to take those coefficients into account, and that is equal to a value of 4.86 times 10 to the negative 6 as given on the previous slide. So we plug in our variables. We have x for the concentration of calcium, 0.1 plus 2x for the concentration of hydroxide, and again set that equal to our value for KSP. And we can simplify this by dropping the plus 2x because our value for KSP is pretty small, 10 to the negative 6, and so we can make this easier by dropping that value. So we get x times 0.1 squared equals KSP 4.86 times 10 to the negative 6. This leaves us with x equals 4.86 times 10 to the negative 4 as our molar solubility. And this can be compared to the molar solubility in pure water, which is 0.11 molar. So you can see that high pH has significantly decreased the solubility of calcium hydroxide. So this brings us to our next topic, which is the effects of pH on solubility of compounds. So we know already from our previous example that the pH of a solution can affect the solubility. With calcium hydroxide, we saw that a high pH led to a decrease in solubility. But what would happen if we had a low pH? So with a low pH, we would have a high concentration of acid. Well, you might imagine that if we have a high concentration of hydronium, that's going to react with the small amount of hydroxide that is present in a solution of calcium hydroxide, and it's going to react to produce water, so it's going to remove the hydroxide from the equilibrium. So if we go back to our original equilibrium expression, calcium hydroxide breaks up to calcium 2 plus 2OH minus. If we decrease the amount of hydroxide, that's going to cause the equilibrium to shift to the products. We're removing a product, equilibrium is going to shift right to the products. So because the products are the ion components, this means that the calcium hydroxide will be more soluble at a low pH. So this gives us another generalization we can make, that is that the solubility of an ionic compound with a basic anion will generally increase with decreasing pH. So in a more acidic environment, something with a basic anion will be more soluble. So this is generally compounds that contain carbonate or sulfate or of course hydroxide. And there are anytime you have a basic anion, you will see this effect. So let's take a look at some compounds and determine whether they would be made more or less soluble in acidic solution. So we start with ammonium chloride. Now we know that NH4 plus is a weak acid, and so adding that to a more acidic solution is going to actually make it less soluble. We also can look at silver chloride. Silver chloride, silver plus, will not react with an acid, and we know that chloride is the conjugate base of a strong acid, so that's going to be a neutral ion. So we will actually see no effect on the solubility of silver chloride in acid. Calcium carbonate, however, carbonate, we said, is a weak base. It's the conjugate of carbonic acid, which is a weak acid. And so we will see an increase in solubility for calcium carbonate in the presence of acid, and the same goes for lead sulfate. Again, sulfate is the conjugate of a weak acid. And just to clarify, you might think, oh, well, isn't that the conjugate of sulfuric acid? Actually, the conjugate of sulfuric acid is going to be bisulfate, or HSO4-. So SO4 2- is the conjugate of a weak acid. HSO4- is the conjugate of a strong acid, so it is going to behave as a weak base. So next we're going to look at the opposite of solubility, which is precipitation. So solubility is when we have a solid going to ions. Precipitation is when we have ions going to a solid. So precipitation happens when two ionic solutions mix to form an insoluble solid, which we often call a precipitate. And when will this occur? When does precipitation occur? There's a couple of ways we can think about this. The first is going to be with solubility rules. So we learned some solubility rules last semester, and these will give us a basic idea of when we have two things mixing together that are going to form a solid, that it's possible for them to form a solid. But then we also need to take a look at our reaction quotient. So even if we have two things we know are going to form a solid, say we've added some silver and some chloride ions, we still have to look at our reaction quotient, or Q, and we're going to compare that reaction quotient to our value of KSP. By comparing those, we can predict if precipitation will occur. So if our reaction quotient is less than KSP, we will see that more solid can dissolve. The reaction can continue to go towards products. And so that would be known as an unsaturated solution, and we will not see precipitation. If we have a reaction quotient Q that's equal to the equilibrium constant, that means the reaction is already at equilibrium, so you won't see precipitation occur. However, when you do see precipitation is when the reaction quotient is greater than the solubility constant. So when Q is greater than KSP, that means that there's too much ion present and the reaction will shift back towards the left, therefore towards the solid, so you will have solid precipitating out. And just a reminder, Q is the same expression as KSP, just not at equilibrium. So let's take a look at a specific example and see if precipitation will occur here. We have a solution of lead nitrate, which is mixed with one containing sodium chloride. So we have PbNO3 plus NaCl, and this is an ion exchange reaction, so our products will be lead chloride and sodium nitrate. We balance that equation. So we want to look here and see if anything ticks off for our solubility rules, and indeed lead chloride will form a solid. Pretty much anytime you see lead, it's going to form a solid. So that's going to be the possible precipitate for this reaction. So next we can write our solubility equation for lead chloride, which lead as a solid dissolves to form lead 2 plus and 2Cl minus. So from that we can write our reaction quotient expression. So again, that's going to be the same as the expression for KSP, just not at equilibrium. So that will be the concentration of Pb lead 2 plus times the concentration of chloride squared. And then we can plug in our values to this expression. For the value of lead, we're going to use 0.15 molar because that's the value of concentration of lead that's been put in. So our Q will be 0.15, and then our concentration of chloride will be 0.035 molar. Again, we're going to square that, and that gives us a value of 1.84 times 10 to the negative 4 molar, sorry, not molar, unitless, 1.84 times 10 to the negative 4 for our Q. So Q here is going to be greater than KSP. And as we said previously, when Q is greater than KSP, the reaction will shift left, which means that in this case precipitation will occur. We will see solid form. So let's look at another example and see if precipitation will occur here. Here we're mixing silver nitrate and potassium iodide, and we want to know if that's going to form a precipitate. So again, we can write our initial reaction. Silver nitrate plus lead iodide produces silver iodide and potassium nitrate. And again, we see that silver iodide is present, and silver iodide, by our solubility rules, will form a precipitate given the right conditions. So we write our dissolution reaction. Silver iodide yields Ag plus I minus, and we can write an expression for our reaction quotient, which would be Q equals the concentration of silver times the concentration of iodide. We can plug our values in. We have 0.1 molar silver, 0.015 molar iodide, and this gives us a value of 1.5 times 10 to the negative 3 for our reaction quotient. So once again, we have a reaction quotient that is greater than Kc, much greater in this case, and so the reaction will shift left towards reactants in order to rebalance it, which means that we will see precipitation occur. So now we're going to shift gears a little bit and talk about complex ion equilibria. So first thing we need to talk about is what is a complex ion. A complex ion is an ion that contains a central metal ion, which is the metal is acting as a Lewis acid bound to one or more ligands. So you're probably asking now, well, what's a ligand? A ligand is a neutral molecule that acts as a Lewis base. So for example, if we have silver plus in water, it doesn't just exist as silver plus by itself, because silver is a pretty good Lewis acid. So instead, water, which is a pretty good Lewis base, is going to bind to the silver. And that's going to form what we call a complex ion. And in this case, that complex ion is going to be silver with 2 water molecules bound to it, and that ion will have an overall charge of still +1. So complex ions can have many different Lewis bases. It can be water, it can be ammonia, sometimes it's cyanide, but they always contain a metal bound to a ligand. And as you might expect, since we're talking about solubility equilibria, this is also an equilibrium reaction. And the type of equilibrium constant here is the formation constant. So the formation constant, or Kf, is the equilibrium constant for the formation of a complex ion. So whereas with Ksp we had our solid breaking apart, the formation constant, Kf, is going to be 2 things coming together to form a larger ion. This occurs because when a stronger Lewis base than water, water is an okay Lewis base but not very strong, things like ammonia are pretty strong Lewis bases and can displace water. So when that happens, we start with our water complex like we stated on the previous slide, and say we added 2 moles of ammonia to that. The ammonia would kick the water out, so you'd, instead of water bound to silver, you'd have ammonia bound to silver, and then you would have water still around. And so all the species in here except water are going to be aqueous. Complex ions do not exist as solids, they are aqueous compounds. And the formation constant, the equilibrium constant for that reaction would be 1.7 times 10 to the negative 7. Oh, sorry, 1.7 times 10 to the positive 7. I've gotten so used to negative equilibrium constants here. So as you can see, that's a pretty large equilibrium constant, and so the reaction is going to favor products. And we often write these reactions in a simplified form where we leave out water. So you would just have silver plus ammonia yields the complex ion, silver with 2 ammonia bound, still with a charge of 1 plus. Always remember that the charge on both sides of your equation should be equal. So next we're going to look at some specific examples of complex ion equilibria and the concentrations of species that will be present in those solutions. So for example, we'll start with a 125 milliliters of a solution that is 0.0117 molar nickel chloride, and that's going to be mixed with 175 milliliters of a 0.25 molar ammonia solution. And that's going to form a complex ion of nickel and ammonia, where 6 ammonia molecules will be bound to nickel. So what we want to find out is what will the concentration of our nickel complex ion be after this solution reaches equilibrium. So first, of course, we'll start by writing out our reaction, just like with any equilibrium system. So we're going to have nickel 2 plus 6 ammonia is in equilibrium with nickel bound to 6 ammonia. And all species here again are aqueous, so there's nothing can be left out of our equilibrium expression. The first step we want to find out is the concentration of nickel, of our nickel complex. Before we can do that, though, we need to find out what our concentrations of each species in the solution are, because we're given the solution, the concentrations of the solution pre-mixed. So we're going to need to use a dilution equation in order to do this. So we'll start by looking at the concentration of nickel 2 plus. And again, the dilution equation we used for concentrations before and after dilution would be M1V1 equals M2V2. So that's the concentration initially times the initial volume is equal to the final concentration times the final volume. In this case, our initial concentration is going to be 0.0117 molar nickel chloride, and our initial volume is 125 milliliters. I'm going to convert that to liters. It's going to be 0.125 liters, and that will be equal to our final concentration, which is what we want to find, times our final volume. Now our final volume should be the total volume of the solution. In this case, that's 300 milliliters or 0.3 liters. So here I've added the 125 milliliters of one solution to the 175 milliliters of the other. If we solve that for M2, we get 4.88 times 10 to the negative 3 molar. Then we're going to set up the same expression for ammonia. Or we would if we actually needed to know the concentration of ammonia. In this case, because this formation constant is so large and there's clearly much more ammonia than there is nickel, we start with 0.25 molar ammonia versus 0.0117 molar nickel. We can say that all of the nickel present is going to be converted to our complex ion, and therefore the concentration of our complex ion is going to be equal to the concentration of nickel. So the concentration of our complex ion is going to be 4.88 times 10 to the negative 3 molar. Our concentration of nickel would then be very close to zero. Not quite zero because that would disrupt to the equilibrium, but it will be very, very close to zero. Almost all of the nickel will be converted. So what if we wanted to find out the concentration of the remaining ion, the remaining single ion, after a complex ion has formed? So let's try another problem like that. Here we have a solution of copper nitrate being mixed with ammonia to form a complex ion of copper and ammonia. So our first step again will be to write out our equilibrium expression, copper 2 plus 4 ammonia is in equilibrium with our complex ion. Make sure that you are balancing the amounts of ammonia in all of these equations, or the amounts of whatever ligand is attaching to our metal. So again, our first step will be to find the initial concentrations. So for copper 2 plus, we're going to use M1V1 equals M2V2, so our initial concentration 0.0015 molar, and our initial volume will be 200 milliliters or 0.2 liters. And that's going to be set equal to the final concentration, which is what we're solving for, times the final volume, which is the total of both solutions mixed together, or 0.45 liters. And when we solve for that, we get our final concentration is 6.67 times 10 to the negative 4 molar. Then we're going to do the same thing for ammonia in this case. We're going to set up a rice chart with our equilibrium expression, so we're going to need all the concentrations. And here we start with 0.2 molar times 0.25 liters. Again, solving for M2 with the solution has the same total volume of 0.45 liters, and we get that M2 equals 0.11 molar ammonia. So now we have our equilibrium concentrations. We can use them or our initial concentrations for our equilibrium system, and we can use that to set up a Rice chart. So of course the first part of a Rice chart is going to be the reaction. Copper 2 plus 4 ammonia is in equilibrium with our complex ion. Next we will put in our initial concentrations. For copper, that's 6.7 times 10 to the negative 4. For ammonia, that's 0.11, and we start off with no complex ion present. So this is where it's going to get a little bit different from what we've done in the past with Rice charts. That's because we know that we have a very large Kf, and so we can assume that the reaction is going pretty much to completion, which means that all, or just about all, so the reaction goes to completion, which means that just about all of our copper 2 plus is going to be converted to complex ion. So we can assume that our complex ion concentration is going to increase by approximately the concentration of the copper, which is 6.7 times 10 to the negative 4. And we can also assume that our concentrations on the reactant side are going to decrease by the same amount, by 6.7 times 10 to the negative 4, approximately. So what does that leave in our equilibrium column then? It seems like we have it all figured out, but as I said previously, there is going to be a tiny bit of copper 2 plus left, and so that amount of copper 2 plus left is going to become X. Our equilibrium concentration of ammonia is going to be minus, don't forget your stoichiometry like I just did, 4 times 6.7 times 10 to the negative 4. And then our concentration of copper is going to be, again, 6.7 times 10 to the negative 4. For ammonia, the number we get is still going to be small enough that we can assume it doesn't actually affect our concentration. It's just going to be, and we're going to be left with 0.11, because that number, even though we're multiplying it by 4, is still so small. So our equilibrium values can then be plugged into our expression for Kf. So we would have our products over reactants, so our complex ion concentration divided by the concentration of copper times the concentration of ammonia, of course raised to the 4th power, and then we would plug in our equilibrium values there. So 6.7 times 10 to the negative 4 over X times 0.11 to the 4th. And again, Kf is 1.7 times 10 to the 13. So a huge value for Kf. So we would expect X to be pretty small. And indeed, when we solve our equation for X, we get that X equals 2.7 times 10 to the negative 13 molar. So that is a very small value, a very tiny amount of copper 2 plus remaining. So this is a tough kind of problem. It's kind of different from the problems we've done before. So we're going to go through another example. You may want to pause the lecture here and try to work out the problem on your own before continuing to see how I work the problem out. Once again, our first step is going to need to be to find the initial concentrations of our reactants so that we can plug that into our equilibrium. So we know we start with copper 2 plus, and the concentration of copper 2 plus we can again use our dilution equation. So we'll start with 0.01 molar copper and multiply that by the initial concentration, 0.5 liters, and that will be equal to the final volume times the total concentration, which will be 1.0 liters. So we get there that our new concentration is 0.005 molar. We can then do the same thing for to find our concentration of NH3. Here we start with, in this case we are working with cyanide, so Cn minus. Again, that's the concentration of our ligand, so that will be 1.0 molar times 0.5 liters, and that will be equal to our final concentration divided by our total of 1 liter, and here M2 will be equal to 0.5 molar. So now we can take these initial concentrations and plug them into our equilibrium expression and use a Rice table to find how much copper 2+ is remaining. So of course we start with our reaction. Copper 2+ plus 2 cyanide ions yields our complex ion. And then we put in our initial concentrations. We have our initial concentration of copper we calculated 0.005, and our initial concentration of cyanide at 0.5 molar. And of course we start with no initial complex ion. So here we're going to say we have a large Kf, so just about all of our copper is going to be converted to complex ion, so that's 0.005 molar. It's going to be because there's 2 cyanides for each copper, that will be minus 2 times 0.005, and then for the formation of the complex ion, approximately 0.005 molar complex ion will form. Again, we make our equilibrium value of copper 2+ X, and we end up with 0.49 molar cyanide and 0.005 molar copper complex ion. We can write our expression for Kf. Again, it will be our complex ion divided by the concentration of the copper times the concentration of the cyanide squared. Don't forget those coefficients. And then when we plug in our values here, we get 0.005 over x times 0.49 squared, and that can be set equal to 1 times 10 to the 16. This gives us an x value that's equal to 0.005 over 1 times 10 to the 16 times 0.49 squared. And then finally, when you solve for x, you get 2.08 times 10 to the negative 18. So that's very, very tiny, super small value of concentration of copper that is left over. Pretty much all of our copper is converted to the complex ion, the copper cyanide. So how do these complex ion formations affect the solubility of other compounds? The answer is that usually the solubility of a metal cation will increase in a presence of a Lewis base that forms complex ions with it. So for example, if we add ammonia to a solution of silver chloride. So if we think about our dissolution of silver chloride, we know that only a very small amount is going to dissolve, and it's going to dissolve to form silver plus and chloride minus. The Ksp for that is very small, so only a very small amount of silver ion will be present. What happens if we add ammonia to this? We know that that very small amount of silver ion is going to want to bond with the ammonia to form a complex ion, which is silver with 2 ammonia atoms bonded to it, or 2 ammonia molecules rather. So this is going to be removing silver ion from our first equation. We'll call these equations 1 or 2. So equation 2 is going to occur and remove silver plus from equation 1. And as we know, if we remove a product from a reaction at equilibrium, our reaction will shift to products. And in this case, the products are the dissolved ions, and so we will see more. The products are the dissolved ions, so we will see more of our silver chloride become dissolved. So we hopefully remember when we did the Le Chatelier Principle Lab back a few weeks ago, we had a system similar to this where we precipitated out some silver chloride and then added ammonia to that, and we saw that that caused the precipitate to dissolve, and that's because the complex ion was forming in this case. So that'll wrap up my lecture for today. I hope this wasn't too difficult to listen to. New technique for me, but make sure to come to class tomorrow and do the worksheet to get practice on these kind of problems. They're kind of tough problems. And as I said in class, there just may be an example problem from this worksheet on the final.